All right. So go to the sorting assignment is first off. I'm giving you your freedom now, which is that you can now work in any programming language you want for the remainder of the assignments. Okay. So any programming language is fair game. So if you want to use R, you can use R. If you want to use Python, you can use Python. Right. That being said, it might be better to use Java or Python just simply because they have the for the graphing problems. Basically, you've got the sorting assignment. You've got the first. Do you have a working graph library assignment, which all you have to do is implement breadth first search and depth first search, and that's fairly easy if you have a working graph library. And then your last one is a security problem that you have to use topological sort to solve. So here, sorting assignment, this is the latest one I gave out. All right, so let's go ahead and take a look at it. This one is a bit different because normally I don't tell you to go out and like look at code and try to figure it and go and say, hey, the code is online so you can look at that. Normally, like you're told, don't look for answers online. This is the exact opposite. This one we're telling you, hey, you should totally look online for the answer. I am just not having a good day. Apparently my mouse is out of battery. So, first getting technical. Oh, there we go. All right. So you're going to implement 3 different sorting algorithms. And you can select them from, so you're going to be doing insertion sort, quick sort, and then you get to choose one other sorting algorithm of your choice. So shell sort, merge sort, heap sort, or tim sort. All 4 of these are in the book. I went over merge sort and heap sort, so let me just briefly tell you about shell sort. Shell sort is this weird multi-layer insertion sort that you insertion sort over certain gaps. Now what makes it very interesting is that I can't tell you what the runtime of it is because it's an unsolved problem in computer science. The worst case runtime is O of n squared, but it depends on what your gap size is. So if you go by gaps of power of 2, it's O of n squared, but we can actually reduce but if you go by gap sizes of O of n, if you go of gap sizes of 2 to the, if you go by gap sizes of powers of 2, so 2 to the kth power, then it's O of n squared. But if you go to the 2 to the kth power minus 1, suddenly it becomes like n of 3 over 2, so 3 root 2. So it's a very interesting runtime for that one. Unsolved problem in computer science, how fast it runs. Or you can go over tim sort, which was invented in 1993. It is probably the newest algorithm in your textbook, and it has replaced merge sorts, I think, as one of the default sorting algorithms in Java, and it's one of the default sorting algorithms in Python. If you implement tim sort, it's worth 7 points of extra credit. It's a combination of insertion sort and merge sort, bringing the best from merge sort and the best from insertion sort. So you're going to be implementing these 3 algorithms. You can probably find code for them in your book. But you need to make some small modifications to them. The first is that you need to keep track of the number of comparisons. So every time you compare 2 items, you gotta keep track of, you gotta increment a counter by 1. Then keep track of the number of exchanges, right? Anytime you swap 2 items, you gotta keep track of that. And thirdly, I want you to keep track of the total runtime when you run the algorithm, right? So then what you're going to do is that once you've written your algorithms, they work on either arrays or lists of any size, right? I want you to collect data because the overall for this is I want you to basically present to me like a table or a graph that shows me, well, at size 100, it was the runtime, it took this many steps to complete, this many exchanges, this many comparisons, and this amount of time, but at size 200, it took them this many times. At 400, it took this many times. You want your data points to actually go over quite a broad range of sizes. So and actually, I would suggest going well above 1024 as your highest size. Don't be afraid to try these for millions, right? Once you confirm this is working, right, that you can collect the data, you can pretty much set it to run for a couple, for like an hour or something, right, as it collects the data. Also, I would have it print out its progress periodically just to make sure it isn't like frozen, or so you know that you didn't give it too big of a size, right? But just like the index tree assignment gave you experience with working with large files, here I want to give you some experience with working with large, with programs that might take a long time to run, which is you get it working for the small sizes, program it to run the big sizes, hit the run button, and then tell everybody you're working while you're playing some video games or watching TV, right? Right? So now you want to probably output your data to file. You could output it to your console, but remember your console can only hold so much. So if you output it to a file, right, I don't expect it to be bigger than you can hold in the console, but if you output it to a file, something like a CSV file, who knows what CSV stands for, by the way? Comma-separated values. Finally, somebody knows. The other two classes, nobody was able to really speak up and say that. It's just a regular text file, so a .txt file, only with a different extension name, .csv. And that means that basically has data separated by commas on each line. It's if you're making a table. If you double-click on it, it will open up like Excel or the equivalent on your system. So it makes it a really easy way to import things into Excel if you want to graph it, right? So you collect data, right, and you get a lot of leeway on how to do it. But generally, like, print out, but if you're lost, like, print out, here's the number of items, here's how many the exchange it took, the number of exchanges, the number of comparisons, and the total runtime. And finally, you got to be able to demo it. Here you're going to present your data to us and tell us, like, which algorithm is better, which of your three algorithms are better on which cases, Ideally, it's something that a non-programmer would kind of understand, right? That you can kind of like point to them and say, and they can kind of tell, as long as you basically told them having less is better, right? So some options include having a well-formatted table or graphing your data. If you don't know how to print something out, you can find that in Appendix A of your textbook, right? Or online, like how do I write to a file, right? How do I write to a file in Java? You can find that in Appendix A, or you can find it on Stack Overflow. That's pretty straightforward. But this is one of those other operations that's fairly straightforward to do once you do it once. All right. So the grading: 20 points for doing insertion sort, 30 points for implementing quick sort, and 20 points for the third sorting algorithm of your choice. Right? You get to choose that third one. Quick sort is a bit tricky because of the partition one, so that's just worth a bit more. So it's 70 points just for implementing the algorithms, which no excuse for not doing that. Then collecting your data is worth 15 points, so long as your data is collected, and then 15 points for presenting it in a meaningful way, right? It's not enough that you can present it. It's got to be in a format that I can actually read and go, aha, I know what I'm looking at, as opposed to, what is this? It looks like gibberish, right? So if you implement TimSort, it's worth 7 extra points, which is the second to last opportunity for homework extra credit. You'll get one more for implementing Dijkstra's algorithms for the next assignment. So, all right, so that's that for the, and right, when I say of your choice, it's one of these 4, by the way, right? Unless you really want to, you see a sorting algorithm you really want to try to do a comparison of, then you're more than welcome to email me and as for an option, but one of those 4 should do. Now, what I want to do before we go over a quiz today, and we have a small quiz today, is I want to go over one more sorting algorithm that I find very interesting that's not in the textbook. That is one of my favorite sorting algorithms, and it's one of my favorites because it doesn't fit the paradigm. We can't really compare it to our other sorting algorithms, not that well, because all the other sorting algorithms work with comparisons, right? We are comparing one number to another number, right? And then swapping them if they don't meet some criteria, right? Or we're always swapping them if they're out of order, but rather the criteria is what order we're going to be doing these comparisons in. So I'm going to present to you Radix sort, which has no comparisons whatsoever. Radix sort is a sorting algorithm which works without any sorting comparisons. You can find it on Wikipedia. In fact, we'll look at the page in a bit. But it's a very interesting algorithm, and it's one of my favorites. So let's take a look at the runtime of Radix sort. It is O to the WN. Now, W is kind of sort of a constant, but it's not a constant we can ignore because it's dependent on what our input is, right? It's still dependent on what our input is, and it's called word size. So if we are dealing with, if we're sorting numbers, specifically if we're like sorting 7-digit decimal numbers, okay, then W is 7, right? Or if the biggest word, or if we're sorting a bunch of numbers and the biggest number is a 7-digit number, then W is 7. If we're sorting a bunch of strings and the biggest string is 20 characters long, then W is 20. It's the biggest word, essentially, right? It's the biggest thing where the length of the thing is W. The length of the biggest thing is W. Does that make sense to everybody? So it makes it very different. And then N, right, the number of input items you have. So how does this work? Well, I'm going to run this over 3-digit numbers, okay? So 3-digit decimal numbers to be specific. So let's start out with, let me go ahead and go with 1, 2, 3. I'll also do 4, let's go with 423. Let's go with 22. Notice I'm pre-padding that I'm pre-padding 22 with a 0, right? That's just simply, that's for simplicity's sake here, so I don't make a mistake. Let's go with 94 as well. And 500, let's go with 473 and 123. And let's see, I'm just trying to get as many. And let's go with 170 as well, okay? So these are the numbers. Now the way that radix sort is going to work, we're working off of decimal numbers. So we are going to create 10 cubes, 10 of them, one for each possible value for a decimal number. Right? If we were dealing with binary numbers, we'd be creating 2 cubes because there's 2 possible values. If we were dealing with just sorting words that were all lowercase letters, then we'd be creating 26 cubes. But we're dealing with decimal numbers, so we're going to create 10 cubes. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So we've got 9 cues here. We've got 10 cues here, one for each number. Okay? So now we go through this and we're going to put each number in the appropriate queue. The way we do that is that we look at the least significant digit of each number. So 123, that's going to go into 3 queue because its least significant digit, it's 1's place, ends with 3. So 123 goes into 3 queue. 1, 2, 3 goes into 3 queue. 423 is also going to go into the 3 queue because it ends with a 3 as well, right? 022 is going to go into the 2 queue because it ends with a 2. 094 is going to go into the 4 queue. 473 is going to go into the 3 queue because it ends with a 3. And 170 is going to go into the 0 queue. Okay? So all the items are in the queue, right? All n items are in the queue, so that run through took O of n time, one for each number. And so now we go through the queues one at a time, from the smallest to the biggest, and we just simply output them back into our list. So 170, 022, right? Because why 022 next? Because we start with the 0 queue, then there's nothing in this queue, then we go to the 20 over here. Then we have 123, then we have 423, then 473. And the reason they come out in that order is because that's the order they just happen to go into the queue, right? And then 094. Okay, so that's our first pass. It's not really sorted, although if you look at just by the last character, it's sorted according to the last character. It's sorting according to the Z, right? 0, 2, 3, 3, 3, 4. But we got to sort it by the whole thing. So the next step is we are going to. Why am I getting so many phone calls? All right. So the next step is we are going to sort based on the middle character, the middle digit. So we're going to just throw them into queues based on their middle digit. So 170 goes into here. 022 goes here because the middle digit's a 2. 123 also goes in here because its middle digit is a 2. 423 also goes in here because its middle digit is a 2. 473 goes into the 7 because its middle digit is a 7. And 094 goes into the 9 queue because its middle is a 9, right? Everybody see how it just simply matched up based on what its middle digit is? Right? Sorry for writing small over here. I keep forgetting that it needs to be like 022, 123, 423, right? Just to make it bigger. And now we go through the queues again and output everything. So we got 022, 123, 423, 170, 4773, 094, right? So now it's sorted according to the. Now, if we were just ignoring the hundreds place, everything's sorted, right? If we were to ignore the hundreds place, 22, 23, 23, 70, 73, 94, right? And so, any guesses what the next step is? Put it into the hundreds place, right? So now we put 022 over here. We put 123 over here. 423 into the 4 queue. 170 into the 1's queue. 473 into the 4's queue, and 094 into the 0 queue, and then we just output it again. And sorry for the small writing again. So now we dequeue 022, 094, 123, 170, 423, 473. Now I like this. So this took 3 basically run-throughs because they were 3-digit numbers, right? Right? So if we had a 4th digit, we'd just do another run-through for that, right? And you can do it from the most significant digit. I just like going from the least significant digit because that leads it to be stable, meaning if that 2 numbers are the same value, right? Say you have 5A and 5B, then in the output, 5A is going to come before 5B, right? That's what it means to be a stable sorting algorithm. So I like doing it that way. But it's really nifty because A, this is a data structures class, and it's a sorting algorithm that uses a data structure to solve its problem. And B, it has no comparisons, right? Now, mind you, most of the time you're dealing with sorting like integers, right? And integers are 32 bits. 32 binary digits, which means that it has a big O runtime of O of Wn. Well, if W is 32, this is 32n, right? 32n, which is typically greater than n log n, right? That's typically bigger than n log n, right? Because the log n part is typically going to be smaller unless you're dealing with literally billions of items you have to sort. Plus, there's also the overhead of creating these queues, right? So you've got that memory wastage going on there. But, it actually has an interesting use case, right? Which is, so if we look up radix sort, and yes, I know I have to turn this back on. We look up radix sort over here, right? If you don't have to compare 2 numbers, then this is perfect for machines that can't do comparisons, right? That can only, like, when you're building something that's just automatically dropping things into slots that can't do comparisons, or not in the way that, not in like logical comparisons, then that's great. Here is a IBM card sorter. It does radix sort. It puts cards into 1 of 13 piles. Right? And apparently you've got a crank over, you put them in around over here, and it dumps them out over here as they come out. And here are just simply previous outputs that get stacked over there. So this is if you want to build something that's physically sort stuff, and then this is the way to go, because it doesn't have to do anything but simply go, oh, it's got punched cards, it's got punched holes over here, so it's going to go into this slot. So this is the kind of sorting algorithm that's used for those kind of machines. So it's a really cool sort. Doesn't really get too much covered, but I like teaching it because it does stuff. It works so much differently than the other sorting algorithms. So, all right, but that's Radix sort. It's not going to be on an exam or anything. It's just useful and valuable information for you to know that there's just just because our best runtime is n log n, that doesn't mean that it's the only option out there, especially not if you're building something that's a physical machine. Not that I expect you guys to be spending thousands of dollars in learning how to basically engineer some kind of like gear crank machine or something like that in your spare time. All right, so with that said,